I put together here, I was asked to put together some work that I'd done with Alex and talk about astrochemistry. And I really wanted to include the first work I did with him, and so I decided as a theme to hold kind of the pieces together. I would talk about atomic molecular probes and to astronomical environments. And really, all the information we have in astrochemistry, I mean, all the information we have about our universe comes to us from, oops, just zooming along without me. This is a disaster. Yeah, let me go back. Anyway, I'm going to just do it this way. It'll be better anyways. We'll see the whole thing. All the information we have in our universe comes to us from electromagnetic processes, and the best information comes from atoms and molecules as probes. They give us our best information because they emit in discrete lines, and we can model those lines and model the chemistry. I'm going to talk about some chemical probes using the chemistry to probe, but I'll start out just by going over astrophysical probes. Actually, let me start out with this, actually. This was actually a book Alex recommended I read when I was running out of reading material one time, and so I'll start with a quote from it. A good friend is someone who visits you while you're in prison, but a very good friend is someone who will come to hear your lectures, which I think is particularly true right now. Well, this is basically a Wien's talk. The way we learn about the universe around us is by taking laboratory astrophysics, which includes both theoretical and laboratory data, and modeling that together to interpret astronomical spectra. And I thought I'd mention as well, there's a nice book by Dalgarno and Laser, Spectroscopy of Astrophysical Plasmas, which goes over a lot of this. Basically the atoms work well, and molecules, because they have these discrete energy levels, and so they emit in discrete lines, and we can model those. And this is a simple two-level atom. Most of you have all seen this. And do you have a pointer by any chance? Could I borrow? I will bring one. Thanks. They emit in discrete lines. Collisions can carry it up between the lines, and collisions carry them back down. Can spontaneously decay and emit a photon. Photons can excite the upper level, and photons can also do stimulated emission, which gives us lasers. And this means that if we have this atom in an environment and it's got collisions with a certain, we'll be carrying it up. And basically the collisions are going to try to push it towards the matter temperature. The radiation is going to push it towards the radiation temperature. Oh, this is terrible. There we go. And we can use these then along with chemical models to figure out what's going on. It can get complicated pretty fast. Even when you get up to diatomic molecules, there's lots of rotational states within each vibrational state, and then lots of vibrational states. But it's interesting, and here's a cosmic background of the cosmic ray background radiation. I thought I'd bring this up just as an example. But in fact, CN was detected in 1938 by Adams using Mount Wilson, and in 1941, Andrew McCullough used the observations to infer that the rotational temperature of CN was about 2.7 degrees. And in fact, we now know this was our first detection of the cosmic ray background radiation, this 3-degree background radiation. It was done well before Gamow predicted in 48, but of course no one really understood they detected it, and they didn't really understand where this excitation was coming from. They assumed it was collisions at the time, but in fact it's coupling with the radiation field, with the cosmic ray background radiation field. And then of course many years later, in 1965, Penzias and Wilson detected it with their microwave telescope and won the Nobel Prize. But in fact it shows kind of the power of laboratory astrophysics, that this detection precedes that by many years. It's just a matter of understanding. Here's a paper in '97 by Guy, Bechtold, and Black, where it's a little bit hard to read on here, but basically the vertical axis is the background temperature. The horizontal axis is redshift. And here they've analyzed, actually it's rather than CN, it's carbon, atomic carbon in absorption against distant quasars, and they've put other people's analysis on. But you can actually use this two-level kind of atom to measure the radiation field, the cosmic ray background radiation field in other galaxies that are, many millions of light years away and back in time. And it works pretty much as expected. But I want to talk particularly about chemical probes, and in fact it goes to the first project that Alex suggested for me when I first came to CFA, and that was that we re-look at the deuterium chemistry. This had been done by Watson in '76, analyzing the DCO plus HCO plus ratio in order to defer the cosmic D to H ratio. And the changes he wanted to do was, he, in doing some work actually with Croswell, had realized that in fact there was a lot of atomic deuterium in these clouds, and people hadn't included that. And so in addition to fractionation from molecular, from HD, you're going to get additional fractionation from atomic deuterium. And this was during this kind of oscillation period where we thought H3 plus was slow. I mean, it was fast in its dissociative recombination, and then some measurements suggested it was slow. Now it's back to being kind of reasonably fast again. Let's look at Watson's work, and we'll see what he did. Basically, the fractionation comes from HD plus H3 plus, transferring the deuterium to the H3 plus to make H2D plus. And this reaction goes both ways, but because it's more bound on this end, it goes faster that way than that way, depending on temperature. And so for low temperatures, you can get quite a large enhancement of H2D plus this way. It's mediated by the fact that H2D plus actually reacts with other things. I mean, it reacts with all kinds of neutrals in the cloud to make deuterium things, and for instance, with CO to make DCO plus. And in fact, it's the DCO plus to HCO plus ratio which he analyzed. But it's also mediated by dissociative recombination. If you just work it out without the atomic deuterium, you get something that looks like this. Basically, it's just all the ways of making H2D plus, which is that reaction listed just before, and there's the forward rate for that reaction. There's the backward rate for that reaction, and here's the other things that can destroy H2D plus, either reacting with a neutral or dissociative recombination. And we took that and modified it by adding in additional processes that have to do with atomic deuterium. In particular, the DCO plus is made additionally by this reaction. The atomic deuterium can just swap itself in directly, and the HD could as well, but the atomic deuterium is quite enhanced. And the atomic deuterium can just swap itself in directly for the H3 plus ion. This atomic deuterium comes from the fact that these molecules are fractionated in the first place. And so the argument seems a bit circular. The reason you have a lot of atomic deuterium is because DCO plus recombination frees up an atomic deuterium. And I should say, because this confused some people, I remember the first conference I went to, someone came up to me and he said, "Oh, I saw your paper with Alex, and it was quite interesting, but it was completely wrong." And I said, "What do you mean?" And he said, "Well, you said that the atomic deuterium affects the fractionation, but in fact your atomic deuterium is coming from the fractionation, and you can't do both." And so I'd like to straighten out the argument here again. And basically his argument was, well, if the atomic deuterium is coming from the fractionation, that is to say DCO plus dissociative recombination makes an atomic deuterium, it's just as if you hadn't destroyed a DCO plus, because then it just goes back to make another DCO plus. And he said, so therefore you wouldn't get any additional fractionation. And I said, well, I mean, we didn't look at it that way, but if you want to look at it that way, the additional fractionation comes with the fact that you don't destroy DCO plus, whereas you do destroy HCO plus, because when HCO plus recombines, you're counting it as gone. When DCO plus recombines, you're not counting it. And so this atomic deuterium really comes in and enhances the thing. the DCO plus, HCO plus rate, particularly at low densities, the atomic deuterium can be high. And we analyzed a number of clouds. Actually, these analysis isn't completely correct because the H3 plus recombination rate is rapid, and we'd used a low value for it at the time. But that only affects the upper limit, and actually leaves the lower limit unchanged. Lower limit being assuming nothing else can destroy DCO plus. And you can see that we can look at quite a few clouds and infer an a total D to H ratio that's pretty consistent in numbers sort of like on the order of 1.5 times 10 to the minus 5, sort of several by 10 to the minus 5. And varies around the galaxy, but not by a huge amount. In order to check these sort of hand calculations, I actually started putting together a chemical model, which eventually grew to 100 species and 1,000 rates. And we analyzed a lot of stuff with this chemical model, but I really want to pick sort of simple and sort of closed small probes of the thing. And in particular, one of the things we added to this chemical model, which actually Aveen mentioned, is the cosmic ray photodissociation rate, which was done with Emil Sternberg. But when we did that, we also noticed something else inside the chemistry, and that something was this, that if you looked at the oxygen chemistry, the oxygen chemistry was entered by H3 plus O, and then you have a series of rapid reactions, taking OH plus to H2O plus to H3O plus, which dissociatively recombines either to H2O or OH. And then OH was primarily removed by reactions with atomic oxygen. And so you have this kind of loop where it's like pouring water from one bucket to another. It has to run through all the way to the end. And you can just figure out how much is coming into this, which is the density of oxygen, the density of H3 plus times that rate coefficient, with how much is going out of this, and relate the OH plus to the H3 plus abundance. There's corrections to this because, of course, it's never quite all that simple. And in fact, sometimes C plus can be important in removing OH. And these cosmic ray induced photons can, in fact, change H2O plus into OH plus, H2O into OH. And so it becomes messier. But basically, putting it together, you get that the H3 plus abundance should just be the ratio of those rate coefficients to the OH abundance with small corrections. And the rate coefficient at the time gave us a number of a tenth. And this allowed us to infer the H3 plus abundance in these clouds well before they were measured. Okay, well, I want to go on and talk about one more atomic and molecular probe. And of course, the main reason that atoms make good probes are these things, and the main thing the probes tell you is that the molecules are there in the first place. And one big shakeup for astronomy was a telegram came into CFA here in 1987 announcing a new supernova had been discovered down in Chile. And this is the picture of that was the discovery picture. It was found by Ian Shelton, was taking photographs of the sky. And he took a photograph one night, and there was nothing there. Took a photograph the next night, and boom, there's a new stars appeared, a bright star. And he realized he'd found a supernova and sent this telegram to CFA. It's rather unfortunate he didn't notice that arrow the night before, because he might have known something was about to happen. Here's a better picture of it taken from the But 1987A was the first supernova that was visible to the naked eye since the invention of the telescope. It's also the first supernova that has been detected in all wavelengths, and in fact been detected in neutrinos. It's the first supernova where we know which star it came from. We know the progenitor star, and we have observations of the progenitor star, and it's the first supernova where molecules were observed, and so we naturally went to model it. The supernova is the death of a massive star. And basically, a massive star at the end of its life looks something like this. I mean, it started as a collapsing cloud, collapsed down until the core was burning hydrogen up to helium. But then it burned all the hydrogen up to helium in the core collapsed again and burns helium up to carbon. Burns all the helium up, the core collapses again and starts burning carbon to oxygen, or actually carbon up to neon, which decays to oxygen. And then collapses again, burns oxygen to silicon, collapses again, burns silicon up to iron. But now iron's the most tightly bound of the elements, and so you're not going to be able to keep powering the star by burning iron up to anything, and instead the star blows up. And this iron core collapses away, makes a neutron star, kicks off the ejecta. The ejecta is additionally heated and ionized by radioactive decay by cobalt-56 that was made during the explosion. And it's rich in heavy elements. It's expanding so that the density is getting lower linearly. It's quite like actually the older universe, which is another thing that Alex and I had modeled and at the time. So we sent our work on this to try to model initially the CO abundance, and then we started looking around for other things out of our model that could possibly be detected. And one of them was HEH+, and it's formed in the supernova same way as it's formed in the early universe by helium plus H radiative association, making HEH+, and it's destroyed by going on to make H2+ by reacting with proton transfer with hydrogen atoms, and it's destroyed by dissociative recombination. And I grabbed the spectra after we saw how much HEH+ we had, and this is a picture of that, and brought it into Alex's office, and I said, oh, here's where the vibrational bands of HEH+ should be. I've colored them in green here. You can't see it too well, but it's the two colored in part. This is a hydrogen recombination line, and this is a hydrogen recombination line. And Alex asked me, well, what about these lines here? What's this line and this line? And they were actually unidentified at the time. And so he said, well, it's going to be hard to convince people that you found HEH+ if you don't know what this is right next to it for things. But he said, but he'd take it along, and he took it along to University College London, talked to Tennyson, who was working on H3+, and in fact, we had modeled H3+ as well. As I said, you get some H2+ made by HEH+ reacting with neutral hydrogen. You can get it, you can go to make H2+. You can also make some H2+ by excited state. I mean, either n = 2 or n = 3 atoms of hydrogen just reacting initially with ground state ones to make H2+. And once you've made the H2+, then some of them will transfer and make H2 with, by reacting with atomic hydrogen. And once you've made atomic molecular hydrogen, then you go on to make H3+. And those fit just with the spectra that Tennyson had recently calculated. And so we put together, this is from our paper with Miller, Tennyson, Dalgarno, and Lepp. And this is that line which I previously had colored in. That's the HEH+. But you can see that this line that was unidentified is actually filled in quite nicely by H3+ emission. And the H3+ emission is consistent with the amount that we had in our models to the extent that we understood it. And here we propagate it through the entire spectra. And again, the H3+ doesn't emit any place it shouldn't emit, and does emit and fill in quite a lot of the material that is. Here's those two lines. You can barely see them on this diagram here of HEH+. But this was really the first detection of H3+ outside our solar system, was in the supernova 1987A. And if you believe the HEH+ detection, it's the first detection of HEH+ outside the laboratory. And so with that, I'd like to just say, you know, atoms and molecules make great probes. It's this sort of mixture of laboratory astrophysics calculations of atomic and molecular data thrown into astrochemical models that, as Evine did so nicely in her talk, lets us talk about how the universe is and lets us help to understand our universe. And with that, I'll say.
Bigger entities as well. Right.